Hi everyone, welcome to all of you on my YouTube channel. So here I am Ankit Misra. I am going to start with the marathon series of heat transfer here. So after that, I'll be doing for all the subject within this week only before get exam. So let's start with the heat transfer. So before going to the concept, first I'll discuss about the number of questions that is going to ask in this year in 2025. So the questions will be from conduction, convection, and radiation. So from conduction, convection, on an average, you can see 3 to 4 questions will be there, and from radiation, approximately 2 to 2 questions will be there. So out of that, this subjects approximately 10 to 12 marks overall, right? Okay. So now, when we see the heat transfer, so heat is energy in the transit, and the transfer of it takes place from higher temperature to the lower temperature object, right? So let's say here if you'll see that in case of potential energy, so the potential energy there, the driving force is the height, right? That is h2 minus h1, right? So whenever there is a difference in energy, then the gradient will be there, and whenever there is a gradient in there, then the transfer of energy takes place from higher level side to the lower level side in potential energy. The same case happens with the heat transfer also. So heat transfer takes place from higher temperature to lower temperature side, and you can see that whenever there is delta T is greater than 0, then only heat transfer will take place. And if delta T is equals to 0, means T1 minus T2 equals to 0, that is T1 equals to T2, then the rate of heat transfer will be 0, means the object will reach into the thermal equilibrium. So from this graph, you can see that temperature versus time curve for two different objects. One object is at 100 degrees centigrade, another is one at 0 degrees centigrade. And with respect to time, you can see the higher object is losing the heat, and higher temperature object is losing the heat, and lower temperature object is gaining the heat. And at a certain time, or after a certain time, what will happen, they both will reach to the equilibrium where there won't be any heat transfer takes place, something like that. So here is another application of heat transfer, where you can see that a metallic ball is having mass mb and heat capacity cp is being placed in water having temperature is T, and the temperature of water is 0 degrees centigrade, and temperature of metal ball is 100. And due to this particular reason, you can see that the metal ball will lose heat and the water will gain heat. So the temperature of metal ball with respect to time will fall down, and the temperature of water will with respect to time will increase. And from here you can see that you can balance the heat, that is Q lost by a metal ball, that will be equal to heat gained by the water, right? This kind of things can happen. So if I'm talking about heat transfer is a non-equilibrium phenomena. Uh, so if you talk about rate of heat transfer, that we generally study in both thermodynamics and heat transfer, but in thermodynamics generally it happens at equilibrium condition, but in heat transfer you will see this is happening at non-equilibrium condition, right? Now coming to the mode of heat transfer, all of these are basic fundamental, just I'm letting you to build up the concept, and after that, based on this, I'll be talking about more and more detailed or depth concept of the heat transfer that will be asked in the gate examination this year. So this is just a revision series for the heat transfer. So now coming to the mode of heat transfer. So obviously we all know that there are three mode of heat transfer: conduction, convection, and radiation. You can see also here in the slide. And the conduction, in conduction, you can see that conduction happens in both solid, liquid, and gases. And conduction in solid, if I am talking about, then solid can be divided in two parts. First is metallic solid, and another one is non-metallic solid. So in metallic solid, you can see that the mechanism of heat transfer by conduction is happening due to the free electron as well as the lattice vibration. But in non-metallic solid, only free electron is not available. That's why the conduction of heat takes place only due to the lattice vibration, right? So, so if you'll see that two mechanism works in case of a metallic solid, and only one mechanism works in case of non-metallic solid. So obviously the rate of metallic solid will be good conductor of heat and electricity compared to the non-metallic solid, right? Okay, so now coming to the effect of the temperature on thermal conductivity. Later on, I'll discuss about the definition of the thermal conductivity. Here right now, just try to understand what is thermal conductivity. Means this is the ability of transfer of heat by any subject object. Right. So here you can see that if you are going to increase the temperature, the thermal conductivity of the object is decreasing. Right. This is the general case. Right. And why this is happening, I'll tell you. But the one exception is that in case of aluminum, so you can see that thermal conductivity of aluminum is increasing with respect to the temperature. If you are increasing the temperature, right? So aluminum is the exception here. Now coming to the conduction rate of heat transfer by conduction in solids. So the mathematical formula that is given by Fourier's that indicates that rate of heat transfer is directly proportional to minus of temperature gradient, and rate of heat transfer is directly proportional to the cross-sectional area through which the heat transfer will take place. So here you can see that cross-sectional area will be something like that through which heat transfer is taking place, which is the perpendicular to the along the direction of the rate of heat transfer. So if you club both of these equation, you will get q dot is directly proportional to, or q dot will be equals to minus k dt by dx, where q dot is rate of heat transfer, k is thermal conductivity, a is the cross sectional area, and dt by dx is temperature gradient along the direction, right? So now you can see that once you solve these things, you will be getting q dot will be equals to T1 minus T2, where T1 is the temperature at the left boundary and T2 is the temperature at the right boundary of the solid having thickness is L, and T1 minus T2 by L by K. So that is delta T, T1 minus T2 is the temperature gradient and temperature difference, and divided by L by K, that is the resistance in the flow of heat transfer, right? So this works similarly like the this is very analogous to the current flowing in the conducting wire. So you can see that there is a potential difference between the resistance, and in between there is a resistance. So if any current is flowing through this resistance, then the potential drop will be there, and the current magnitude of current that can be calculated as delta V by R, and that is delta V is V1 minus V2 by R, where R is the resistance and V1 V2 is the potential difference between the two ends. So similar phenomena happens with the heat transfer also, where Q dot is rate of heat transfer, which is analogous to the current in the electric current circuit, and T1 minus T2 is the temperature difference, and L by K is the resistance in case of heat transfer that occurs in case of current also. So resistance in a conducting solid having thickness is L and thermal conductivity A K, and cross sectional area A will be equal to R by L by R equals to L by K. So this question was asked in GATE 2024 by ISC Bangalore. This was very simple question, but again you can see fundamental questions can be asked in the GATE also. Okay, so now when we define the thermal conductivity K, that can be equals to Q dot divided by A into minus dt by dx, means the rate of heat transfer in a solid having cross-sectional area is 1 and temperature gradient is 1, then the rate of heat transfer which is occurring in a solid will be called as the thermal conductivity. So this is just a standard thing, and you are standardizing the thing there. And from here, you can calculate the units of thermal conductivity, K is watt per meter Kelvin, right? This is very simple. Now, here you can see that in case of solid, if left boundary is at temperature T1 and right boundary is at temperature T2, and thickness of the solid is L, where temperature T1 is greater than T2. So obviously, rate of heat transfer will take place from higher temperature to lower temperature side, and that is the phenomena that due to this heat transfer happens. So let's say this particular equation can be used, Fourier's law of heat conduction can be used to calculate the temperature at any location within this particular solid, inside the solid. So if you integrate this equation, dt by dx equals to minus k by q by k, you will get equation like t equals to minus q dot by k x plus c1. And you have two boundary condition, that is when x equals to 0, temperature is c1, and when x equals to L, temperature is t2. And from here you can calculate the value of constant also c1. And finally, you will get the value of temperature at any particular location x along the direction of the heat transfer, that is equals to T1 minus Q dot by K into x, where this follows the linear equation relations. So this is just a equation of linear equation, straight line equation, y equals to mx plus c, where m is equals to minus q dot by k, and t1 is the the intercept. So due to this particular region, this equation, you can calculate the temperature within the solid at any particular location x while using this thing. So the question can be asked graphically or numerically. All of these things already I have told you. So the thing that is going to click you there, you can use that kind of thing now. Now coming to the general heat conduction equation in 3 dimension. Obviously, derivation is not going to be asked in the examination, but how the derivation is being developed, and how you can perform the derivation. If you forget the formula, then definitely it is going to help you a lot, and because this is very, very fundamental concept of the heat transfer in by conduction. So here I have assumed that cubical shaped solid having length of the side is delta x, delta y, and delta z. So differential volume I can calculate delta x, delta y, and delta z. And after that, you can see that, let's say along x direction, if heat transfer is taking place, this one will be the cross sectional area, right? The yellow thing that you can see, and the value of this one will be delta y and delta z. And again, rate of heat transfer takes place from along y direction and along that z direction, having respective surface area will be cross sectional area will be equals to dx dz and dx dy. So let's say if I'm balancing the if I'm doing the heat balance along the x direction, so if the thickness along x direction is q dx, so the heat which is going to enter, rate of heat transfer which is entering at left bound is q dot x and right bound is q dot x at x plus dx. And similarly, you can write along y and z direction. So if I'm writing the energy balance equation here, that energy in minus energy out plus energy generation minus energy consumption, that is equals to energy accumulation, right? This is very, very important equation, and very frequently you can see that in chemical engineering we are using either in terms of chemical reaction engineering or in terms of in heat transfer. Sometimes we are using in process dynamics and control also. So when I'll be, taking the marathon class of PDC, that there I'll be discussing all of these things. So here you can see that along x direction, how much energy is getting into rate of heat transfer is q dot at x, and along y and z direction also q dot y and q dot z respectively. And energy out, which is coming out of the cubical volume at x plus dx, y plus dy, and z plus dz is equals to q dot at x plus dx, q dot y at y plus dy, and q dot at z plus dz, right? So once we do these things, so we can do the Taylor series expansion of q dot at x plus dx, that is equals to q dot at x plus q dq dot x by dx and dx. And similarly, I can perform these things for q dot y plus dy and q dot z plus dz. So now I am going to assume that q dot g is the energy generation per unit volume within the solid, right? So obviously, in the above formula, you have seen that we have to use this equation, that energy generation. So total energy generation in the differential volume will be equals to volumetric heat generation multiplied with the differential volume, that is q dot z into dx, dy, and dz, right? So accumulation of energy in the within the solid, that will be equals to d by dt of the internal energy of the solid. So internal energy can be written as mcpt. And what is the m of the differential volume mass? That is rho into volume. So rho is there and differential volume is there. So you can write rho into cp into volume and dt by dt. So from here we have you can write this energy, that is energy balance equation, energy in minus energy out plus generation equals to accumulation. Here I have assumed generation is there, that's why q dot is volumetric heat generation. So there may be consumption, so you have to write minus q dot multiplied with dv, that is the volumetric heat consumption with negative sign. So once you put all of these things here, you will be getting that you will be getting this kind of equation, that d by dx of kx dt by dx and d by dy of ky dt by dy plus d by dz of kz dt by dz, that is equals to q dot g, which is equals to rho cp dt by dt. This is just coming from the mathematical expression that we are simplifying these things, and we are getting this thing. But this equation is only valid when kx is the function of temperature or x, right? But if kx is constant, if I am assuming kx, ky, and kz is constant along any direction for the isotropic solid, so here you can see that kx, ky equals to kz equals to k. So after that, this will come out of the differential, and directly you will see d2t by dx square plus d2t by dy square plus d2t by dz square plus q dot g by k equals to rho cp upon k into dt by dt. Okay, so now coming to one parameter, that is alpha, that is k by rho cp. So alpha is the ratio of thermal conductivity by rho cp. So this is the ratio of heat transfer by heat storage. So let's say if any material having higher alpha value, means heat transfer will be more, and if any material having very lower value of alpha, that is thermal diffusivity, means heat transfer will be less compared to the heat storage, means that material will be very inclined towards the storing heat compared to the transferring of the heat. Okay, I hope up to now all of these things are clear to all of you. After that, I'll be moving towards the limitations of this equation. So whenever I'm seeing we see this equation, that this equation is a three-dimensional heat conduction equation in Cartesian coordinate having volumetric heat generation in q dot g at unsteady state condition. And here what we have assumed that cross-sectional area along the direction of heat transfer is constant first. Second thing is that thermal conductivity of the material along any direction, all the direction was constant, that means kx, ky, and kz was equals to k. And after that also we have assumed that this is only valid for Cartesian coordinate, and the volumetric heat regeneration q dot g is there, right? And thermal conductivity was also constant. So once we since this is the three-dimensional equation, but if I want to reduce this equation in terms of one dimension, you can see that d2t. I mean, I'm just neglecting that heat transfer along y and z direction. So you can reduce this into one dimension, that is due to d2t by dx square plus q dot g by k equals to 1 upon alpha del t by del t. So this equation is valid for one dimension volumetric heat generation at unsteady state condition, right? But if I want to again reduce this equation in terms of a steady state condition where temperature is not the function of time, so you can see that del T by del tau equals del temperature divided by del T equals to 0. So ultimately this equation will get reduced in the form of d2T by dx square plus q dot g by equal k equals to 0. So now while using this equation, you can calculate temperature within the solid at any particular location, right? And temperature will be a function of x. Now, moving towards the next thing, if there is no heat generation, if no heat generation is there, then definitely Q dot G will be 0. So the ultimately this equation will get reduced in the form of d2T by dx square will be equal to 0. So this is just a homogeneous second order differential equation. And in order to solve the homogeneous second order differential equation, you know the value that you will require two boundary conditions. So here you can see there are two boundary conditions. When x equals to 0, temperature is given T1, and when x equals to T2, temperature is given as T2, right? X equals to F. And once you solve these things, you will get that there is a linear equation. This equation is looking like an equation of a straight line, that is y equals to mx plus c, where tx is equals to t1 plus delta t into x by l. So you can see that the slope is there and intercept is there. So let's say if temperature versus x curve is given, you can calculate slope is equals to t2 minus t1 by l, and obviously intercept is t1. T1 is the temperature at the left boundary, and t2 is temperature at the right boundary. And from here you can calculate the slope, and once you calculate the slope and intercept, you can calculate the temperature of the solid at any particular location, right? So with that, this equation is very very helpful, I mean very very important, and questions can come from here. Now, coming to the volumetric heat generation, if volumetric heat generation is there in the solid, right, at a steady state condition. Now, once you do the calculation, and this is again second order ordinary differential equation, and in this equation also require two boundary condition to get the value of the constants, because you will get two constant here, C1 and C2. Once you substitute this value, you will be getting constant value, and finally you will be getting this kind of equation. So this equation is not very important. I won't suggest you to remember this equation, but again, once you know the mathematics, then definitely this will be very easy for you and you can solve these things in your examination also. But here the most important thing that you can see, whenever there is a volumetric heat generation or volumetric heat consumption in the solid at a steady state condition, you will see there is a parabolic temperature profile, right? So that is function of x square by 2, something like that. Okay, so you will see a parabolic temperature profile. So you have to remember, when there is no heat generation, the profile will be linear. When there is heat consumption or generation, the profile will be your parabolic. And later on, I'll show you the graph how the temperature curve will look like in case of solid when there is a volumetric heat generation or consumption is there. Okay. Now, till now, I have assumed that thermal conductivity of the material was constant. That's why this was coming out of the differential, right? But now, when the thermal, I mean, every time in the real case scenario, thermal conductivity is not going to constant. It can be a temperature, function of temperature, or function of your x value also, means the location also, right? But let's say here I am assuming thermal conductivity is function of temperature. That means K equals to K naught into 1 plus beta T. There is a linear relation of thermal conductivity with temperature. Means if you will increase temperature based on the value of beta, the thermal conductivity will increase and decrease. We'll see later on how these things are vary. This is going to vary with respect to the temperature. If value of beta is going to changes from negative to 0 and 0 to positive, right? Okay, so in the master equation that I have showed you earlier in terms of one dimensional and a steady state heat conduction equation, if I'll substitute this thing, K equals to K naught into 1 plus beta T, and from here you can get the d2T by dx square equals to minus beta into del T by del x whole square upon 1 plus beta T. So now you can see that the slope of temperature versus x curve here, that is going to depend upon the value of beta, and obviously this will be a positive quantity, and minus beta upon 1 plus beta T, right? So you can see that this is going to vary up, based on the beta. So if beta is positive, then definitely this d2T by dx square will be less than 0. And if beta is negative, then d2T by dx square will be 0. And if beta will be 0, then definitely d2T by dx square will be equals to 0. So if you plot these things, you can see that if I am plotting temperature versus x for varying thermal conductivity with temperature, you can see that when beta is less than 0, this will go like that, and when beta will be 0, then will follow the linear curve that already we have discussed, and when beta is greater than 0, you can see this curvature things will be there, right? So this shows when there is no heat generation and conduction within the solid, and beta is a function of temperature only, right? Now coming to the next part, where you can see that curve 1 and curve 5, that is red curve and green curve, is going beyond temperature T1 and it is coming less than temperature T2, right? So if it is going more than temperature, highest temperature, then definitely heat is getting generated in the solid. Curve 1 shows that heat is getting generated in the solid, and beta is also, sorry, thermal conductivity is also function of temperature, right? And the green curve shows that since temperature is going below the lower temperature, means definitely there is a heat consumption inside the solid. So obviously this shows, the graph shows there is a heat consumption in the solid as well as temperature, thermal conductivity is function of temperature. Okay, so this will be the case. Okay, that is very important. And now, since we have seen that thermal conductivity is function of temperature, so you have to calculate the mean thermal conductivity somewhere else. And the mean thermal conductivity formula that you can use here is T1 to T2 and kT dt upon T2 minus T1. So kT will be equal to 200 minus 40T, right? So let's say if you have this kind of variations of thermal conductivity with temperature, you can use this formula, and ultimately you will be getting this kind of answer. So again, this formula is also very, very important. This can be asked in your examination. Okay. Okay. Now moving towards the next question, thing in heat conduction in solid. So we have different boundary condition is there in the solid, and based on the boundary condition, the problem may be different, right? So let's say first boundary condition is a specific temperature boundary condition. So in this boundary condition, you can see that both the temperature of the left hand side and in left surface and right surface of the solid will be known to you. Means let's say at x equals 0, temperature T1 will be given, and at x equals 12, temperature T2 will be given. And already we have seen this kind of case in earlier problem or earlier concept. Okay. Now, moving towards the next case, next boundary condition, sometimes they can give you that a specific heat flux boundary condition, and on the both surface, that is left and right, that is x equals to 0 and x equals to L, you can see that heat flux is given to you QL and QR, right? And you can use these things. This is the second boundary condition. Third boundary condition is convective flux boundary condition, where you can see that there is a rate of heat transfer by convection is happening along the left surface, and after that you can use rate of heat transfer by conduction, and then on the right surface you can see that rate of heat transfer is acting due to convection. So from here you can see, when if I want to write the boundary condition at x equals to 0, so you can write rate of heat transfer by convection equals to rate of heat transfer by conduction at the left boundary, and H8 T infinity is the surrounding temperature or bulk temperature, and H1 is heat transfer coefficient towards the left side. So HA T infinity minus T1, that will be equals to minus K dt by dx. Here you have to calculate the temperature gradient at the left surface, and you can use these things. And again, similarly, you can use at the right surface also, something like that, where you can see these things. Okay. Now, coming to the interfacial boundary condition, where you can see that temperature of the left and right surface will be given to you, and sometimes thermal conductivity of two materials will be given, and both of these are brought in contact with each other, and sometimes you are supposed to calculate the temperature at the interface. So what will happen, since the cross-sectional area of both of these materials are same, and the thickness is, let's say I'm assuming is delta L and delta L is same, so definitely only heat transfer will be taking place due to the conduction. So rate of heat transfer from object 1 to 2 will be equals to Q1 dot equals to Q2 dot. So rate of heat transfer by conduction, you can directly use Fourier's law of heat transfer, minus K1 A1 dt by dx at x equals to 0, that is equals to minus K2 A2 dt by dx at x equals to 0 only at the interface condition. And once you do these things, you will be able to calculate the interfacial temperature while using this formula, right? So from here you can see dt by dx is the temperature gradient in object first, and dt by dx 2 is the temperature gradient in object 2. So rate of heat transfer is same, and if let's say K1 is greater than K2, right? So in that case, if both of these things have to be equal, then definitely slope 1 is will be less than slope 2. So sometimes they can give you this kind of curve, and you are supposed to calculate if slope is more in first and compared to second, then thermal conductivity relations, right? So these kind of questions can be asked, but only you have to understand if two quantities multiplication are same, then how these things can vary. So sometimes analytical skills will be required here, so you have to think in that way. Okay. Okay, so I hope up to this everything is clear to all of you. Now coming to the next boundary condition, that is symmetric boundary condition. This is very, very important boundary condition to understand. So in symmetric boundary condition, what will you understand? So in case of solid, if you are drawing any line, So the solid will look like similar in case of left side and right side also. The same case here you can see that at x equals to 0 is the mirror line. So here you can see that at left side temperature at minus L equals to minus T1, and at right side also temperature at L equals to T1. So here you can see that due to this particular symmetric condition you can assume that at x equals to 0 the flux will be 0, means dt by dx temperature gradient won't be there, dt by dx is equals to 0. So here you can get different kind of relation. At x equals to 0, dt by dx will be 0. At x equals to minus L, temperature is T1. At x equals to plus L, temperature will be T2. Sorry, T1. So lots of relations are there, and sometimes they can ask you to calculate various parameters related to that. Okay. Great. So after that, I'll be moving towards the next theory. Here you can say that insulated boundary condition. So in case of insulated boundary condition, what happens? So due to the insulation, there won't be any rate of heat transfer, right? Heat flux will be zero. So if I'm talking about heat flux is zero, means temperature drop will be zero, Tt by dx. Okay? Because thermal conductivity cannot be zero, cross-sectional area will be there. So my out of minus Ka dt by dx, only dt by dx can be zero. Only then, only flux will be zero, right? So in for insulated boundary condition, you have to only use that dt by dx is equals to 0. Okay. Okay. Then it is fine. After that, I'll be moving towards the these things formula for the convection rate of heat transfer, convective rate of heat transfer. So in case of convective rate of heat transfer, you can see that we generally use Newton's law of cooling, where H is the thermal heat transfer coefficient, will be unit will be watt per meter square Kelvin. E is the surface area, and temperature drop is there T1 minus T2, right? Through which heat transfer is taking place. Okay. So here you can see already I have discussed all of these things, electrical analogy thing, and I'm not going to discuss these things again. So sometimes they can give you, object in series combination, parallel combination. So this is going to follow exactly the same concept that we generally follow for the electrical analogy also. That is, in series combination, resistance will get added, and in parallel combination, resistance can be written as 1 by R total equals to 1 by R1 plus 1 by R2 and plus 1 by R3. And resistance in terms of heat transfer, that can be equals to thickness upon Ka. That is thickness of the material, and K is the thermal conductivity of material, and A is the cross-sectional area through which heat transfer is taking place. Okay. Sometimes they can give you combination of series and parallel. So again, exactly this is series, this will be parallel. So you can calculate the R equivalent of this parallel combination. Then all of these three will come in the series, and then you can calculate the series combination only, something like that. Okay. This is very, very important. You can read. Now, coming to the next important concept of rate of conduction heat transfer in cylindrical or variable area geometry, that is called the cylindrical geometry, right? Or cylindrical coordinate. So, Cartesian coordinate is a bit easy compared to the variable area geometry, that is cylindrical and spherical coordinate. But again, questions are coming from this topic, so this topic is also very important. So see here, one thing is that in case of Cartesian coordinate, area cross-sectional area was fixed through which heat transfer was taking place, right? But in case of cylindrical coordinate, you can see that area is not going to fix. Area is going to vary and along the direction of heat transfer, right? So here you can see that if I'm talking about surface area for cylinder, so this is used to be 2 pi RL. So if I am going from center to any radial distance, so radius is going to vary, and due to this variation, surface area is going to vary, right? So in order to understand this particular thing, I'll go at a distance r, and I'll take a differential cross-sectional area element having thickness delta r, and now I can use the energy balance equation that I have already used in case of Cartesian coordinate system, where Q at r minus Q at r plus dr plus generation minus consumption, that is equals to accumulation, right? So here you can see that Q at r minus Q at r plus delta r plus Q dot J into dV equals to d by dt of mCpt. So here differential volume can be written as 2 pi r delta r, right? And obviously you have to multiply with the length of the cylinder, right? So first you will be going 2 pi r into delta r, right? And after that, once you multiply it with the length, that will give you the differential volume of the cylinder up to a radius of thickness of delta r, right? Once you have differential volume, you can calculate the length is there, mass. Mass is rho into differential volume. And now you can write Q at R minus Q at R plus dr plus Q dot is volumetric rate of heat generation in the cylindrical differential volume into 2 pi R delta R into L equals to d by dt of mass. That is obviously I have calculated into CPT. CP is the thermal heat capacity of the material, solid material. So once you do these things, and after that doing the Taylor series expansion, this is very simple mathematics. You will be getting, that is uh, K by R, I am assuming K is constant right now along the direction of heat transfer. So K by R d by dr of R dt by dr plus Q dot G equals to rho Cp dt by dt. This equation is very, very important. Sometimes they can ask you the this kind of formula in your MCQ, which of the following option is correct for the rate of heat transfer. So you can write K by R d by dr R dt by dr plus Q dot G equals to rho Cp by K. So since K is constant, so again we can define the thermal conductivity, and ultimately this formula will get reduced in the form of 1 by R d by dr R dt by dr plus q dot g by k equals to 1 upon alpha dt by dr. Okay, so this is very, very important formula. Questions can be asked from this formula, but again, if let's say at a steady state condition, dt by dt will be equals to 0, and this formula will get reduced in this form 1 by r d by dr r dt by dr plus q dot g by k equals to 0. So now you can calculate the temperature variations with the radius, and ultimately you will be getting that this is a logarithmic temperature profile you are getting with respect to the radius. Right. So in cylindrical coordinate system, the temperature profile will be logarithmic. But when there is a heat, there is no heat generation. Again, here there is no heat generation. Then you are getting a logarithmic temperature profile, and you can calculate the temperature profile something like that. But let's say rate of heat transfer. One second. Hello. Okay, so rate of heat transfer in terms of spherical geometry, spherical coordinate, you can see that if let's say you have a sphere, something like that, and now in this, okay, so now first I'll calculate the rate of heat transfer in cylindrical coordinate first. So once you calculate rate of heat transfer, you can write Q equals to minus K dt by dr, and obviously dt by dr temperature profile, you know, that is C1 ln R plus C2, that is logarithmic profile. So once you substitute these things, you can calculate Q dot is equals to T1 minus T2 ln R2 by R1 divided by 2 pi KL. So first you have to understand what is the meaning of this formula. This is very, very important, right? So when we talk about T1, T1 is the temperature when radius is R1, and T2 is the temperature when radius is R2. And obviously K is the thermal conductivity, and L is the length of cylinder, that is delta T by R0. Okay. So the resistance that is there in case of rate of heat transfer in cylindrical coordinate is ln R2 by R1 divided by 2 pi KL. And resistance, this is due to the rate of heat transfer due to the conduction in the cylinder, right? So finally, again, there can be a concentric cylinder, and in concentric cylinder, you can have, at R equals to R1 temperature is T1, at R equals to R2 temperature is T2, and at R equals to RT temperature is T3. So you will be having two resistance here. One is R1 and one is R2. And since this is working in a series combination, that's why you can add both of these resistance together, and ultimately you will be getting R1 plus R2 equals to R equivalent. And finally, the rate of heat transfer can be written as T1 minus T2 or T1 minus T3 divided by R1 plus R2. So whenever you are taking T1 minus T2, so you have to put that resistance. And when you are taking overall temperature drop T1 minus T2, T3, so you have to put the overall R equivalent, right? Overall resistance. So that thing you have to be very careful in the examination. So just don't be in a hurry while solving all of these kind of problems. Just try to be calm, because definitely this question is will be having 2 marks. So for 2 marks question, you have to be very calm, solve the question very properly. There should be a proper way. Be very disciplined while solving this kind of problem. Okay. Okay, great. So after that, I'll be moving towards the next concept. Again, here are some kind of questions. That questions I'm not going to, discuss, because this is marathon classes for theory only. So I want to be discussing this thing. So let's say if the question is something like that, 1 by R d by dr of R dt by dr plus Q dot G by K equals to 0. So at this is a cylindrical coordinate, a steady state condition when there is a heat generation in the solid, right? So earlier I have discussed the case of when there was no heat generation. So in this case, you can see that this is just a differential equation, and once you solve this differential equation, you will be getting that the formula Tr equals to Q dot G by K into R square by 4 plus C1 ln R plus C2, something like that. Okay. Now, so you have boundary condition, that is because in order to solve this constant C1 and C2, you should have two boundary condition, and obviously two boundary condition is they are there. R equals to R1 when T equals to T1, and R equals to R2 when T equals to T2. Okay. And one more thing that is very, very important, that at R equals to 0, you can see that temperature gradient is 0. right? So these things, once you will incorporate all of these things, you will be getting that temperature variations inside the solid in the cylindrical case, that is Q dot G by 4K into R square minus R square plus Ts. Ts is the temperature of the cylinder at the surface when R equals to R, means at the outer surface, right? So here you can see temperature profile will be a parabolic. So we have seen that temperature profile was parabolic when there was heat generation and heat consumption in case of Cartesian coordinate, as well as when there is heat generation and consumption in case of cylindrical coordinate also, there is a parabolic temperature profile. Okay. So these things are there. So you have to remember both of these cases. Sometimes in examination you will get confused that no, it cannot be a parabolic, but in both of these cases we have observed that parabolic temperature profile is there. This is very important thing, right? So one in 1 marks they can ask you this kind of question. Okay. Okay, great. So after that, I'll be moving towards the next concept here. For the concentric cylinder, already I have discussed, so I am not going to discuss these things. Now coming to the heat conduction by hollow sphere, right? So this is similar to the this concentric, sorry, cylindrical coordinate system. But here we can see, you can see, in case of cylindrical coordinate system, the formula was 1 by r del by del r of r del t by del r plus q dot g by k equals to 1 by alpha del t by del t. But in case of a spherical coordinate, I'm not going to derive, for derivation is not very important here, but formula is there, that 1 by r square. So in case of here power was r, here this will be r square, and only the, and all of these things are matching with the same with the earlier one, right? 1 by r square d by dr, r square d2 by dt by dr plus q dot g by k equals to 1 by alpha dt by dr. Okay. Okay, so when we are going to solve this equation at a steady state and no heat generation, so again you will be having a formula 1 by r square d by dr, r square dt by dr equals to 0. So this is just an ordinary differential equation, and this will be a second order ordinary differential equation. So once you solve these things, you will be getting temperature profile is minus C1 by r plus C2. So y equals to 1 by x is a equation of hyperbola. So this is a hyperbolic temperature profile. And the most important thing that you have to understand here, when you are getting hyperbolic temperature profile, when there is no heat generation at a steady state condition in a sphere, right? In cylindrical case, that was logarithmic temperature profile when there was a steady state condition and no heat generation was there. Okay. So after that, in case of a sphere, what you can see, if you want to drive, you can drive here the way I have derived these things, but derivation is not important. But how to solve this differential equation that you are getting from here, that is very important. So let's say if there is a heat generation in the sphere Q dot G, and at a steady state condition when there is no variation of temperature with respect to the time. And once you do these things, and once you substitute all of these boundary condition, you are also getting temperature profile is Q dot G by 6K R square minus R square plus Ts, right? So here you can see that we are again getting, quadratic, means parabolic temperature profile. So in all of these cases at a steady state condition and when there is heat generation and consumption, we are able to see that in every one case parabolic temperature profile we are getting. So you have to remember these things. Okay. Okay, so after that, sometimes you can calculate the maximum temperature also, because if there is a heat generation inside the solid, so temperature, what will be the maximum temperature? You can also calculate that thing. So maximum temperature can be observed here at R equals to at the center of the sphere, and the temperature will drop. And due to this particular region, you can assume that there will be a spherical symmetrical conditions that at R equals to 0 at the center of the sphere, del T by del Y R equals to 0, that is symmetric boundary condition that already I have discussed in the previous slide. Now, coming to the thermal insulation, this is also very important topic for the gate, and very frequently they used to ask question in heat transfer from this particular topic from thermal insulation. So the purpose of thermal insulation is to save the energy, because obviously if you don't want to lose some amount of heat, because heat dissipation is very money intensive process, right? So you don't want to lose your heat also, and to reduce the heat loss obviously, and to serve so if I'm talking about kind of geometry that we have studied till now in case of heat transfer, the geometry is plane slab, a sphere and cylinder, right? So in case of plane slab, you can see that the rate of heat transfer is happening through a cross sectional area, and the cross sectional area is constant. And yeah, so in case of these things, if you see that if delta 1, delta 2, and delta 3 is the thickness of the insulation here, if I'm adding the insulation in the plane slab, what is happening? thickness of insulation if you are increasing, then rate of heat loss will be decreasing. Means let's say if this one is at higher temperature and atmosphere is at lower temperature. So if you are increasing the thickness of insulation, then definitely rate of heat loss you will be able to decrease. So means it will always going to decrease the heat loss if you are increasing the thickness of insulation in case of plain slab, right? Or cut plain geometry, right? But when it comes to the variable area geometry, that is a cylinder or a sphere, the case will be very different, right? So sometimes you will see that if you are going to increase the thickness, rate of heat loss will increases, and after a certain thickness, it will start decreasing, right? So how these things is happening, will let you know while using this particular concept for the cylinder only. So cylinder is also a variable area geometry where you can see that a cylinder having inner radius is R1 and outer radius is R2, and thermal conductivity of this cylinder and insulating material is also given, and inner surface temperature is T infinity 1 where convection will be happening, and outer surface temperature is T infinity 2 where convection is also happening, and T2 is the outer surface temperature. So you can see that T1 is there, T infinity 1, that is the fluid which is inside of the cylinder, and R conduction is happening, and again R convection will be happening. So you can calculate the conduction resistance ln R2 by R1 divided by 2 pi K L, and R convection can be written as 1 upon H into 2 pi R2L, right? So if I want to write total heat transfer, rate of heat transfer, so T infinity 1 minus T infinity 2, because T infinity is the temperature of the surrounding fluid inside the cylinder, hollow cylinder, and T infinity 2 is the ambient temperature outside. And now once we substitute the R conduction and R convection, okay. Now R2 is the outer radius. So outer radius is going to vary. Why? Because if you will be adding insulation, then only outer radius is going to change. Inner radius will be constant. So if you can see that first rate of heat transfer is increasing and then it start decreasing. So at a particular point you will see that maximum condition is arising. So means rate of heat transfer with respect to radius will be zero. Del Q R by del X will be del R will be equals to zero. Is that clear? So why this is happening, just try to understand. So if I write Q dot, that is equals to delta T divided by ln R2 by R1 divided by 2 pi KL plus this one. So if R2 is going to increase, this one will increase and this one will decrease, right? But if R2, the logarithm of R2 will be very less compared to this one. So what will happen? A rate of heat transfer by convection will decrease fast compared to this one. And due to this particular reason, first resistance is decreasing. So overall resistance is decreasing first. Due to this particular reason, what is happening? Rate of heat transfer is increasing, right? And after that, what will happen when the value of R2 will be very, very high, that will be appreciable value, then this will be very less and this will be very high. Is that clear? So in that condition, what will happen? The rate of heat resistance will start again increasing, and ultimately you can see that Q dot will decrease. That's why you are getting that kind of slope. And once you will differentiate these things, dq by dr2 equals to 0, and the Q dot is the only function of the resistance, right? If resistance is increasing, the Q dot will be decreasing. So it's better to differentiate these things with respect to R2, resistance with respect to R2. And once you differentiate the resistance with respect to R2, so at maximum heat flux condition, what will happen? Resistance will be very minimum. And the minima is in terms of what condition? The parameter will be the outer radius R2. That's why I'm differentiating these things. And once you differentiate all of these things, you will be getting the R2 will be equals to K by H. Means the radius at which the rate of heat transfer is maximum, that is called as the critical thickness, critical radius of the insulation. Means critical radius of insulation up to which rate of heat transfer will increase, and after that when you are increasing the radius of the insulation, again it will start decreasing. So this is the same case that is happening here. And you can see R equals to RC when Ki by H. Okay. So when the outer radius will be less than RC, what will happen? Added insulation will increase the heat loss. When R2 will be RC, then heat loss is maximum. And when R2 will be greater than RC, means added insulation's critical thickness of insulation or critical radius of insulation is less than outer radius, then added insulation will decrease the heat loss, right? So RC is the critical radius of insulation that already I have told you. So sometimes get used to ask what is the critical thickness of insulation. So critical thickness of insulation will equal to critical radius of insulation minus R2. That is the outer radius of the insulation, right? And you can calculate the mod because you are calculating the thickness. Okay, so here you can see that RC minus R2 is the critical thickness of insulation. So you have two parameter here. What is RC and what is RC minus R2? RC is the critical radius of insulation and RC minus R2 is the critical thickness of insulation, right? You have to be very careful about this. Okay, coming to the critical thickness of insulation for a sphere. So again, you can use the similar procedure that I have derived earlier. You can differentiate the resistance with respect to the outer radius. You can make it zero and you can calculate the value of R, and that R will be called as the RC. That is equals to 2 into Ki by H, right? What is Ki? Ki is the thermal conductivity of insulation and H is the heat transfer coefficient for the surrounding fluid, and 2 Ki by H. Okay, that's it. Now I'm moving towards the next and very important concept of the rate of heat transfer by conduction, that is unsteady state heat transfer. Very frequently get used to ask question on this topic. Out of every 10 year, you can see 8 questions are coming from the conduction on this particular topic, right? So when we talk about unsteady state heat conduction, where temperature with respect to time was zero, del T by del T equals to zero, right? But when we talk about unsteady state condition, temperature is going to vary with time. So that's why temperature is function of x and t. When temperature will be both function of space and time, right? So you will observe a spatio-temporal distribution of the temperature is observed in case of solid. Great. Now, coming to the lumped heat capacity system, this is very special kind of system that has been observed in either chemical reaction engineering also in case of heat transfer also. And this is very uh, this kind of topic makes very great importance in industry also. So here you can see that when temperature is function of time and when temperature is not function of space. So in case of lumped heat capacity system, this is an unsteady state condition where temperature is function of time, but temperature here is not function of space. Means dt by dx will be equals to zero everywhere, right? But dt by dt will not be zero, right? So let's say here, if an object, a spherical object or a spherical metallic solid is being placed in the water, so what is happening here? If by any means the parameter is being tuned in such a way that the temperature within the solid with respect to space is constant. So here you can see this is T1, this is T1, this is T1. So at any particular radius, temperature is T naught at T equals to 0. But when at T equals to T1, across all the radius, you can see temperature is changing T1, T1, T1. Again, at T equals to T2, temperature is changing. And is this temperature is changing across a whole solid, not at a particular location. So that's why this system is called as a lumped heat capacity system. And in this case, you can see temperature is function of what? Temperature is function, not function of what? Temperature is function of time only, right? So here you can see that dt by dr will be equals to 0 and dt by dt is not going to equals to 0, right? So if I'm assuming radius of this metallic solid is 0, radius is capital R, density is 0, and at t equals to 0, temperature is Ti, and this object is being placed in the infinite medium having a temperature is T infinity and heat transfer coefficient is H. So whenever heating is there, means if what is the case of heating and cooling? Here there will be two cases. When heating is there, means T infinity will be greater than Ti, and when there is cooling is there, means rate of heat transfer will be taking place from metallic solid to the water, means Ti is greater than T infinity, right? And now when we apply the energy balance, energy in minus energy out is the rate of change of internal energy of the solid. So energy in is how much? Ha T minus T infinity, right? Rate of heat transfer by convection. So since the fluid surrounded by the solid or the solid which is being surrounded by the fluid will be giving heat to the solid. Let's say I am talking in case of cooling case, right? So rate of heat transfer by convection will be equals to decrease in internal energy. So the amount of heat which is being transferred from the solid will be equals to rate of change of decrease in internal energy of the solid, and which will be equals to the rate of heat transfer by convection here, right? So from here you can see H at Tt minus infinity equals to minus d by dt of rho and V Cpt. So obviously you know the volume and surface area of the solid. So whenever we talk about the convection, we write the surface area, and whenever we talk about rho v, so that is the total volume. So once we solve these things, we get that Tt minus T infinity, temperature of the solid at any particular time, minus T infinity, that is the temperature of the surrounding fluid, by Ti minus T infinity, that is equals to exponential minus Ha by rho Vcp into T. So when the solid is losing heat to the atmospheric fluid or the fluid which is surrounding the solid, then the formula here is minus Ha by rho Vcpt. And when the solid is being heated by the fluid, means temperature of the fluid is more than temperature of the solid, then this formula will be positive here. That is the case. So Tt is the temperature of the solid sphere at any time. T infinity is the temperature of the surrounding fluid. Already, obviously, I have discussed. So from here you can see that at t tending to infinity, what will happen? This particular things will be equals to zero, and due to this particular region, what will happen? That Tt equals to what t infinity plus Ti minus t infinity means this will be at t equals to infinite time. What will happen? The solid temperature and the fluid temperature will be getting equated, and the object will start reaching to the equilibrium. And due to this particular region, you can see that the solid temperature is decreasing, and the which is going to reach to the fluid temperature at T equals to infinity asymptotically, right? These things. So here one parameter can be defined as tau, that is rho v Cp divided by Ha, that is called as a time constant. So sometimes you can use this formula Tt minus T infinity divided by Ti minus T infinity, that is equals to T minus T by tau, where tau is equals to rho v Cp by Ha. And once we plot these things, you can get this kind of curve, right? Now the questions can come from here only. Sorry for that. No. Here you can see the question, how they can ask the question from here. So let's say they can ask you the order of tau 1, tau 2, tau 3 if this kind of plot is given to you, right? So from here you can see that the formula. Okay, so here now I'll be going to talk about, now you can use these things very easily. This is very easy thing. Directly you can relate these things while using this formula. So if temperature this one, so how this temperature is going to vary with respect to tau. So you can calculate the proportionality relationship with Tt equals to T infinity plus Ti minus T infinity into T minus T by tau, and directly you can calculate this thing. Okay, so I'm not going to indulge in that thing. So from that formula we can calculate the value of Tt. And now I want to calculate the total rate of heat transfer, right? So from t equals to 0 to t equals to at any particular time t, how much heat transfer was there? So I can calculate Q total, that is equals to 0 to T and QT dt. So Q total can be written as 0 to T and HA TT minus T infinity dt. So I am just assuming rate of heat transfer by convection. And TT we know that Ti minus T infinity into T minus T by tau. So once you do the integration and once you calculate these things, you will be getting the total rate of heat transfer up to time t equals to HA Ti minus T infinity into tau into 1 minus T minus T by tau. So this formula is very, very important. But again, I will suggest you don't remember this formula, but if you know this process, how we are moving, or how we are able to logically derive this particular steps mathematically, then definitely in the examination you can also do in 1 minute and you can write the correct formula. But remembering this formula is very, very difficult because lots of things that will be there in your mind, so I won't suggest remember this formula. Okay. Okay, after that I'll be moving towards one more important parameter, that is Biot number. So Biot number is defined as the rate of heat transfer by convection in the surrounding fluid by rate of heat transfer by conduction in the solid, right? So Biot number is less than zero, then the lumped heat capacity system can be used, right? So here if I derive the formula for Biot number, rate of heat transfer by convection by conduction, you can see that HLC by K, where LC is the characteristics length of the solid object, and the characteristics length formula can be written as volume by surface area of the solid, right? So from here you can see Biot number is less than 0.1, that is valid for the well-lumped capacity system, and means rate of heat transfer by conduction will be less than rate of heat transfer by convection, right? And when it can occur? So when rate of heat transfer by R conduction will be less than R convection, something like that. Okay, these things you can use. So lumped capacity system will be used when Biot number is less than 0.1, when rate of heat transfer by conduction, resistance by conduction is less than resistance by convection, or rate of heat transfer by conduction is very, very greater than rate of heat transfer by conduction. So if rate of heat transfer by conduction is very, very greater than convection, what will happen? That throughout the whole solid at a particular location, you will see the temperature drop is not there, means d3 by dr will be 0, means temperature is not going to vary in the object with respect to a space, right? So when these things can happen, when Biot number is less than 0, when HLC by K is less than 0, and these things can only happen when H is very less, K will be very, very high, and LC will be very, very less, right? So this kind of things can be there. Now coming to the next part of this unsteady state conduction in infinite solid, this formula is also very, very important. Here, in case of infinite solid, earlier in case of lumped capacity system, we have seen temperature was only function of time, it was not function of space. But in case of infinite solid, here in a steady state condition, here you can see that temperature is going to function of time as well as space also. So this profile shows the lumped capacity system where temperature is only function of time, not space. But this profile shows temperature is a function of space as well as time also. So this is also very, very important. And the trend of gate is like they are going to the advanced level. So this is the advanced level of unsteady state conduction time. So if I'm talking about one dimensional unsteady state formula for heat conduction, that is equals to del 2 t by del x square equals to alpha del t by del t, right? So this is unsteady state conduction. So when I am assuming at time t equals to 0, the solid infinite solid temperature is Ti, and this is just a partial differential equation, right? Just remember, because temperature is a function of two properties, two independent variable, that is x and t. That's why this is called a partial differential equation. And here in this case, you can see that once you use this formula, then you can write exactly temperature at any particular time t minus T infinity, that is surrounding flow temperature, minus divided by Ti minus T infinity, that is equals to ERF function, that is error function x upon 2r 2 alpha t, right? So ERF x upon 2 root alpha t. So how they can ask the question? So the value of x, alpha and t will be given. So here you can see that temperature is function of x and t also. So if you are going to change x, temperature will change. If you change t, temperature will change, right? So if let's say x upon all of these value are given and the value of error function will be given to you in the option, sorry, in the problem. And from here you can calculate this value and you will get. So this formula is valid for infinite medium, solid infinite medium, and unsteady state condition. This is valid for lumped capacity system, right? Okay. So obviously this is very, very important kind of problem. So with that, I would like to end this lecture here only. In the next lecture, I will be completing the fins as well as the convection. Okay. Thank you. See you in the next lecture.